Hello friends, here in this video we will see a problem of direct and bending stresses in which we are going to solve it for maximum and minimum intensities of stresses. So here is the question. A rolled steel eye section with top and bottom flanges 200 mm into 20 mm and web 15 mm into 250 mm. Deep is used as a short column to carry a load of 1000 kilonewton. Now, whatever is given here, first I'll write that in the form of data. It is given that it is a rolled steel eye section. So I'll write the name of the section. It is an eye section with top and bottom flanges. The dimensions are given. I'll write down top flange. It is 200 into 20 and even the bottom flange is of the same dimension. Next, web is 15 mm into 250 mm. Then it is used to carry, deep is used as a short column to carry a load of 1000 kilonewton. So I'll write down load as P, that is 1000 kilonewton. So it is 1000 into 10 raised to 3 Newton. Then if the load line is eccentric 50 mm above x-axis axis, this is the centroidal axis for the eye section. So with respect to x-axis the eccentricity is given. So I'll write down it is E suffix x, value is 50 mm and 30 mm left of y-axis, y-axis, that is eccentricity with y, 30 mm. Find maximum and minimum intensities of stresses induced in the section. So the question is to calculate sigma max and sigma min, maximum and minimum intensities of stresses induced in the section. So now with the data in front of us, let us try to get the solution to this problem. It is given that it is an eye section. So first I'll draw the diagram for that eye section. So here is the diagram of the eye section. Next, I'll mark the dimensions over that. Now, here it is given that eye section has top flange of 200 mm into 20 mm. So here the top flange is having width is equal to 200 mm and this depth is 20 mm. Similar dimensions are there for the bottom flange as well. It is mentioned 200 into 20. Next, web, it is 15 mm into 250 mm. So here the width is 15 and this height of web is 250 mm. Now, here if we look into the figure, this eye section we can say that it is symmetric about the y-axis, and it will also be symmetric about the x-axis here. So it means the centroid for this I section is located at the intersection of x and y axis. Now, in the solution part, after drawing the I section, here it is said that a load of 1000 kilonewton, it is placed at eccentricity from x axis. The load is at 50 mm distance, so eccentricity with respect to x, that is, this is the x axis, 50 mm above that we have the load, and with respect to y, it was given that 30 mm left of y axis. So this 30 mm distance is to the left of y. So here I can say that the load would be placed somewhere here. I'll mark the distances. Now, eccentricity with respect to x-axis is here, that is given 50 mm, and with respect to y-axis it is here EY, that is 30 mm. So this is the location of the load. Now, the question is to find the maximum and minimum intensities of stresses induced in the section. So we have to find that for this I section where would be the maximum and minimum intensities, and that we can find out by giving 4 corners, extreme corners for this I section. Here we have A, this corner would be B, next here we have this corner as C, and here it is D. So we would be finding that out of A, B, C and D, at which point there is maximum stress and at which location it is minimum stress. So to find that out, the first thing is we should know the area of this I section. So I'll calculate the area starting the solution from after the diagram. Since cross sectional area of given I section, that will be capital A is equal to, here as we can see in this I section, I divide it into number of parts. Here I'll call it as first rectangle, second rectangle and third rectangle. So I will calculate the area here. So now here I'll get the capital A value. So area will be, here we have 2 flanges and 1 web. So area would be 2 into area of flange, that is 1 flange, plus area of web. Here we have 1 and 3 as the top, 1 is the bottom flange, 3 is the top flange, and here this central part as it is called as the web. So therefore area will be twice into area of flange. We can take any one flange because both of them have same dimensions. So it is 200 into 20 plus area of web 15 into 250. So from this the value of area, it comes out to be 11.75 into 10 raised to 3 mm square. So after getting the cross section area, the next thing is, since as we see in the problem, the load is located at distance Ex with respect to x-axis, at distance Ey with respect to y-axis. So this kind of load, it is called as eccentric load, and because of this eccentric load, here in this I section there will be direct stress because of the load present here. So load upon area will give us direct stress, and because of the eccentricity here, as we can see, it is eccentric with respect to x-axis, so there will be bending about x-axis since the load is located at a distance, so there will be bending about x. Similarly, here we have EY, so because of this EY distance there will be bending about y-axis. So this is a case of direct as well as bending stresses. So here first I'll calculate the direct stress. I'll say that now, since the given load is eccentric with respect to both x-axis, is eccentric with x-axis and y-axis, therefore direct as well as bending stresses are induced in the given I section. So here we have a case of direct as well as bending stress because of the presence of eccentricity. Now first thing is we would be calculating the direct stress. I'll say that therefore direct stress is given by sigma d is equal to P upon A so therefore direct stress becomes, load is given as 1000 kilonewton, so it is 1000 into 10 raised to 3. Area, it is 11.75 into 10 raised to 3. So from this we get the value of direct stress, and my answer is 85.11 Newton per mm square. This is the value of direct stress. Now after getting direct stress we need to find bending stress, and in that bending stress, before calculating that, we should have the value of moment of inertia about both the centroidal axes. Since here we have x axis and y axis, we need to know their distances. So I'll say that as the section is symmetric, this y axis is located at exactly half of 200. So this is x bar is equal to 100 mm. Next y bar, the total height is 290 here, so half of 290, that is 145 mm. This is y bar. So here we have the location of centroid, x bar and y bar values. Now here we would be calculating the MI about x axis and y axis because it would be required in the calculation of bending stresses. So here I'll say that since MI about horizontal centroidal axis is given by, the horizontal centroidal axis is xx, so Ixx is equal to, now here Ixx can be calculated in such a manner that since we can consider this I section as a complete rectangle having width 200, height 290, and from that complete rectangle we would be subtracting these two rectangles. I'll show it with the help of a rough diagram here. Now here for this I section I am considering as a complete rectangle having width B 200 mm and the height is 290. Now from this complete rectangle I'll calculate the moment of inertia about the x-axis for this bigger rectangle, and now from that bigger rectangle I am going to subtract these two smaller rectangles. I am shading here. So if we subtract from the bigger rectangle these two smaller rectangles, I'll get the mi for this I section about the x-axis. So now here when we are calculating the moment of inertia for the I section about x-axis, I am considering it to be a complete rectangle having width 200 and depth 290. So about x-axis the moment of inertia of the outer rectangle will be capital BH cube by 12. From that I am subtracting the moment of inertia for one small rectangle, which is this rectangle. It has a width of, here this is 200 and this distance it is 15 given. So from 200 if we subtract 15, that comes out to be 185, and if we take half of 185, that is 92.5 mm here, and this height is equal to the height of the web, which is 250. mm is the height of web. Now I am going to subtract from this complete rectangle moment of inertia formula, that is BH cube by 12, minus, here we have two such rectangles, so it is 2 into, I'll write it as small BH cube by 12. Now putting the answers, the values here, capital B is 200, capital H is 290, divided by 12, minus 2 into small b, it is 92.5, which is for the small rectangle, and small h, it is height is 250. So therefore Ix value, it comes out to be 165.59 into 10 raised to 6 mm raised to 4. So here we have calculated the moment of inertia for the I section about its x-axis, that is centroidal axis, which is horizontal. Next case, here I will calculate the moment of inertia about vertical axis, which is the y-axis. Since mi about vertical centroidal axis is given by, now here I write down Iyy is equal to, we have three rectangles, we have divided it into, this is the first rectangle, this is second, and here we have third rectangle. So Iyy is Iyy1 plus Iyy2 plus Iyy3. putting the values here, therefore Iyy will be equal to Iyy1. It is the moment of inertia for rectangle number 1 about its y-axis, and as we see, y-axis for the complete I section is located at 100 mm distance, which is x bar. Similarly, the y-axis of rectangle 1, rectangle 2 and even rectangle 3 are passing through 100 mm. So there is no need to use parallel axis theorem. So directly applying the formula, that is Iyy is dB cube by 12, moment of inertia formula for rectangle about the vertical axis. Next, dB cube by 12 for second rectangle plus dB cube by 12 for third rectangle. So therefore Iyy is equal to d and b values. Now for the first rectangle, this d, it is 20 mm and b is 200. So 20 into 200 cube by 12 plus the second rectangle, it has b as 15 and d is 250. So dB cube by 12, 250 into 15 cube by 12, and as the dimensions of first and third, that is bottom and top flange, are same, so here I'll write the same values. 20 into 200 cube divided by 12. So hence my answer of Iyy, it comes out to be 26.74 into 10 raised to 6 mm raised to 4. Now, after getting Ixx and Iyy, the next thing I'll write here is the bending stress formula. So now, since bending stress about x-axis is given by sigma b suffix x is equal to bending moment about xx upon Ixx. I'll keep this as equation 1. Similarly, bending stress about y-axis is given by, I'll write it onto the next page, bending moment about y-axis sigma by is equal to bending moment about y-axis upon, it is bending moment. So here we have, it is m by z, actually this is m by z. So even here we'll have to make a change. In equation 1 it is m by z, because m by z will give us the bending stress. So here I have written equation 1, here we have equation 2. Now as we see in both equation 1 and equation 2, here we want the value of zxx and even mxx, and similarly myy, zyy. So first I'll calculate mxx, that is bending moment about x-axis, that is mxx is equal to load into eccentricity with respect to x-axis. Load is 1000 into 10 raised to 3. Eccentricity was 50 mm with respect to x-axis. So bending moment about xx, that is 50 into 10 raised to 6 Newton mm. Similarly, bending moment about y-axis is equal to P into E suffix y. Load 1000 into 10 raised to 3. Eccentricity was 30 mm. So bending moment about y-axis is 30 into 10 raised to 6 Newton mm. So now, after getting bending moment at xx and yy, we are going to find zxx, zyy, that is section modulus value, because it is required in the calculation of bending stress. So here, since section modulus with respect to x-axis is given by zxx is equal to ixx upon y, therefore zxx is equal to ixx, it was 165.59 into 10 raised to 6 mm cube, because here I has a unit mm raised to 4, y is mm. So here I have written ixx value. First of all, this will be mm raised to 4 moment of inertia. Now I'll put the y value. Y value is nothing but the location of this x-axis, and this x-axis is located at 145 mm. So y is 145 mm. So here mm and mm will get cancelled. So mm raised to 4 will become mm cube, that is the unit of section modulus. So zxx value, this comes out to be 1.14 into 10 raised to 6 mm cube. Similarly, I'll write down the section modulus about y-axis zyy is Iyy upon y, and here we have Iyy as it was 26.74 into 10 raised to 6. Now y value, this y value indicates the location of y-axis. It is at 100 mm from left hand side, because this is the reference. So 100 is the y value. From this I am getting zyy, which comes out to be 184.41 into 10 raised to 6 mm cube. So after getting zxx, zyy, we can put the values in equation number 1 and 2 respectively. So here I'll say that therefore put bending moment at xx and zxx in equation number 1. So therefore sigma b about x is equal to in equation 1 we were having mxx upon zxx. Now I'll put their values. mxx was 50 into 10 raised to 6, zxx 1.14 into 10 raised to 6. So therefore from this I'll get the answer of bending moment, bending stress about x-axis, that is 43.86 Newton per mm square. Now similarly put bending moment about yy and section modulus about yy in equation number 2. So therefore bending stress about y is equal to the bending moment about yy, that was 30 into 10 raised to 6, and now zyy, it is 184.41 into 10 raised to 6. So from this the bending stress about y-axis, that comes out to be, it is 112.19 Newton per mm square Now after getting these values, we can go on for the calculation of the stress intensities at each of the locations. So now after we have got sigma bx and sigma by, we can calculate the stress intensities at each of the corners. And if we look into the problem, they were saying us to calculate the maximum and minimum intensities of stresses. Now if we look at this I section, here out of the four corners A, B, C and D, corner A is that which is closest to the load. So we can say that out of the four corners, corner A or point A is the point where there will be maximum stress, for the simple reason that load is closer to point A. So here I'll write down maximum stress first. Since maximum intensity of stress will be at point A, so therefore sigma max, it will be at A and given by direct stress plus, here as we see, because of Ex there will be bending about x axis like this, in this manner, bending about x, and because of Ey there will be bending about y in this manner. So we have to add sigma bx and sigma by, because all these stresses are acting at point A, that is the addition of all the stresses. Now I'll go on putting the values. Direct stress we have found out, it was 85.11 plus sigma bx 43.86, sigma by 112.19. So from this, sigma max at A, the value comes out to be 241.16 Newton per mm square, and this will be our first answer. Now as this answer is positive, it means that direct and bending stresses, it is the first chapter in which we consider compressive stress as positive and tensile stress as negative. So here if we see in the diagram, because of the load P, there will be compression on the entire member. Because of eccentricity Ex, there will be bending about x axis, and because of that bending, point A will be pressed, so there is compression. Next, about y axis there is eccentricity, so again when the load is acting, there will be bending produced, and that will result in pressing of point A, again there is compression. So here point A is subjected to compression throughout, answer is positive. So I'll write down here this is compressive. Next I'll write down similarly, here if we see the point which is far away from the load, it is nothing but point D, which is exactly opposite, because at a point if you are getting maximum stress, opposite to that the corner will have minimum stress. So here I'll say that therefore minimum intensity of stress will be at point D. So therefore sigma minimum, it is at point D, and that will be direct stress minus bending stress about x minus bending stress about y. So therefore I'll put the values. Sigma minimum, that is at D, is equal to 85.11 minus 43.86 minus 112.19. So I'll get the value as minus 70.94 Newton per mm square. This is our second answer. And as I have told just now that this is the first chapter in which we are taking the compressive stress as positive. Here my answer is negative. It means because of the action of all the load, point D will be lifted. It means there is tension at point D. So here the answer is negative. It means the nature of stress is tensile, which is the minimum stress, and because of that point D gets lifted. So here, as we see in this question, they had asked us to calculate the maximum and minimum intensities of stresses, and that we have found out. Maximum stress at A, which is 241.16 Newton per mm square, and the minimum stress is at the opposite corner, that is minus 70.94 Newton per mm square. And with this we complete the problem.